Hi everybody, in this video we're going to talk about how we can use this expression to find the distance between 2 points in 3 dimensions. So in the real world we live in 3 dimensions, right? We can move right or left, that's one dimension. We can move up or down, that's another dimension. Or we can move forward and backward, that's a third dimension. So we might want to know the distance between 2 points which are separated in real 3-dimensional space. Okay, so let's put one point over here and let's put another point over here. You know, first I should talk about this. You're probably used to seeing, if you've been in my class and watching my videos, a 2-dimensional coordinate plane like this with an x-axis and a y-axis. Over here we have a 3-dimensional grid. But this time, the x-axis is sort of going out of and into the page, or the screen rather. So this is the x-axis over here. This is the y-axis, and this one we'll call the z-axis. So we have 3 axes now. Okay, now so we're working in 3 dimensions, just like real space, right? And let's say that we had a point over here, which would be, what would that point be? That would be -2, 0, 0. Okay, it's at -2 on the x-axis, it's at 0 on the y-axis, and 0 on the z-axis. And let's have another point over here, and what would that be? That would be 0, 3, 4. So that would be at 0, it's at 0 on the x-axis, it's at 3 on the y-axis, and it's at 4 on the x-axis. So you have to think 3-dimensionally here. But right now it's not actually so important what these coordinates are. Let's just focus on the dots themselves and try to think of a strategy. How could we figure out the distance from here to here? And remember, it's not a simple 2-dimensional distance, it's 3 dimensions now. So this point here is coming a little bit out of the screen, you have to imagine, and this point it's like exactly on the screen. So not only is there a horizontal distance between these 2 points and a vertical distance, there's also, let's call it an into the screen distance between them. Okay, so now we have to come up with a strategy for finding the distance from here to here. And what we're going to do first is we're going to find the distance from here, not straight to here yet, but to right over here, which is just below this point along the y-axis. So we're going to find the distance from here to here first. Now, how can we do that? We're going to do that by drawing a right triangle like this. Okay, and you might be looking at that and thinking to yourself, well, wait a minute, Mr. Friedman, this angle that you drew doesn't quite look like a 90-degree angle. It looks a little bit obtuse, right? But you have to be thinking 3-dimensionally. So imagine I took a right triangle and then I sort of pressed it down like this and I flattened it onto a tabletop or something. Then it would end up looking something like this. And this is my right angle right over here. Okay, so I'm going to label this leg A, I'm going to label this one B, and I'm going to label this one C. Now, if you watched one of my previous videos, then you know we can find C by taking the square root of A squared plus B squared, and we can find A and B by subtracting the x values. So for example, this point would have an x value of 0, and this point would have an x value of 2. And we can find the y values we can find b by subtracting the y values. So for example, this point would have a y value of 0, and this point would have a y value of 3. But I'm just going to write the general form, square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so subtracting two y values gives us the length of b, and subtracting the two x values gives us the length of a, and then squaring them and then adding them together and taking the square root, that gives us the length from here to here, which we called c. Okay, so we have a strategy now for finding the distance from here to here, but what we really wanted to do was find the distance from here to here. So we haven't figured that out yet, but what we're going to do is we're going to apply this rule again, which, remember, comes from the Pythagorean Theorem, and we're going to draw another right triangle like this. Okay, so here's the right angle for this right triangle. And again, if this looks like it's not a 90-degree angle, you have to be thinking three-dimensionally. And if you took a right triangle and sort of twisted it like this, and then drew a painting of it, it would come out looking something like this. Okay, so this is a 90-degree angle over here. And so we can label this leg of the triangle D, and we can label the hypotenuse E. Okay, so what we're really looking for is E, which is the distance between this original dot that we had and also this original dot that we had. Okay, now how can we figure out what E is? Well, we're going to apply, you know what, I'm going to keep the same color here. We're going to apply this same sort of rule over here, where E is equal to the square root of C, you know, I don't know why I made that so long. E is equal to the square root of C squared, right? So C is a hypotenuse of this right triangle, but it's a leg of this right triangle, okay? And E is the hypotenuse. So C would go over here with the other leg D. So E is equal to the square root of C squared plus D squared. Okay, but wait a minute. We know what C is. Well, we didn't actually calculate the number, but we have a formula for it right over here. C is equal to the square root of x2 minus x1 squared, blah, 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 blah. So what we can do over here is we can plug that in for our value of C in this equation. And that would give us that E is equal to the square root of C squared. Well, C is the square root of all this. So let's write the square root. So we have a square root inside of a square root, which I know looks pretty weird. So I'm just copying this whole thing for what C is. The square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, but then don't forget, this is C, but in this equation here, C is being squared. So we have to square this whole thing. I don't know if that made it look neater or messier, me putting the parentheses there. But anyway, so this whole thing is C, and then I had to put the exponent of 2 over it. And now I have plus D squared. So D is this side of the right triangle over here. And the way that we would figure out the length here is by subtracting the z components of these 2 points. Just like we subtracted the x components to find the distance here, and we subtracted the y components to find the distance here, we would subtract the z components to find the distance upward in this case. So D is equal to z2 minus z1. And then we'll just copy the rest. So plus this squared, right? Okay, and now what we have here is we have the square root of something, and then we're taking the square of that. Well, what's going to happen here is that the square root and the square cancel each other out. And so what we're left with is this is going to be our final expression for finding the distance between 2 points in three-dimensional space, which is this square root symbol canceled with this exponent over here. So what's left over is just this stuff inside, which was x2 minus x1 squared plus y2 minus y1 squared. And then we also have this plus z2 minus z1 squared. Okay, so that is where this expression comes from. And if we know the coordinates, then we can just go ahead. So for what did we say? We said that this was 2, 0, 0. This over here was the point 0, 3, 4. Okay, so if we know what the let's call this x1, y1, z1. If we know these coordinates, then we can just plug everything into this formula and figure out the distance from here to here. Okay, so let me erase all this now. You can rewind if you want to remind yourself where that came from. Okay, so we have the square root of x2 minus x1, so that would be 0 minus 2, which is negative 2, and then we would square that, plus y2 minus y1, so that would be 3 minus 0, which is just 3, and square that, plus with z2 minus z1, that would be 4 minus 0, which is just 4, okay, and then square that, and that is equal to the square root of negative 2 squared is negative 2 times negative 2, which is 4. So we have the square root of 4 plus 3 squared is 9. 3 times 3 plus 4 squared. 4 times 4 is 16. And that's equal to, let's see, 4 plus 9 is 13 plus 6 is 16 is 29. So the square root of 29. And then let's just go ahead and use a calculator for that, and we'll round our answer to the nearest, let's go to the nearest tenth. What's going on here? This froze for some reason. Try that again. It's going to work now? Okay, square root 29. Okay, so remember, this is the 10th place over here. This is the digit that we would look at if we're rounding to the 10th place. If this is a 0, 1, 2, 3, or 4, then this digit stays the same. If this is a 5, 6, 7, 8, or 9, then this gets bumped up one. So since this is an 8, this is going to get bumped up to a 4, right? 3 plus 1 is 4. So this is approximately, yeah, I should really be changing this to a squiggly equal sign, which means not exactly equal to, but approximately. Square root of 29 is approximately 5.4. Okay, so from here to here would be a distance of about 5.4 units. All right, let's just go ahead and do one more I promise, very quick example. I'm not even going to draw the 3D coordinate grid. Okay, because as long as we have this formula over here, we don't even need the grid, right? So what's the distance between this point and this point? Show your work. Okay, so let me show my work. I'm going to call this x1, this is y1, this is z1, and then x2, which just means the x value of my second point, the y value of my second point, and the z value of my second point. And now let's go ahead and write this expression. So we have, you know what, I'm not going to write the whole thing with the x2 and the x1. You have it right over here. Let's just go ahead and write it this way. So x2 minus x1 is negative 2 minus negative 7 minus negative 2. Actually, it doesn't really matter the order that we write them in. So -7, and then don't forget the minus, so that's this minus over here, and then I have -2. Okay, so I'm going to have two of these symbols right next to each other. Now, it actually doesn't matter which one you put first, so let me just sort of skip ahead a little bit and show you. -7 minus -2 would be -5. But if I'm squaring -5, then I have -5 times -5, which is +25. Okay, what if I had put this one first, instead -2 first and -7 second? Well, then I would get -2 minus -7 would be +5. But +5 squared is, again, 5 times 5, which is 25. Okay, so I get the same answer of +25 here. So because of this exponent of 2, we would have a negative times a negative, which is positive, or we would have a positive times a positive, which is positive. So we would end up getting the same answer here either way. So it actually doesn't, if you fudge it up a little bit and you do x1 minus x2 instead of x2 minus x1, you'll get the same answer. Okay, but I'm just going to do it the way that I have it written over here. So -7 minus -2, and then plus what's my y2? 2 minus 8. Okay, squared plus, then with the z's, -6 minus 3 squared. Okay, so this is equal to -7 minus -2. So minus negative becomes plus. So that's like -7 plus 2. So now if I think about a number line, if I start on the number line at -7 and I do plus 2, which means I go 2 spaces to the right, I would end up at -5, right? Or another way of doing that is, I like to say that if these symbols are different, then what we would do is we would subtract, and we would take the symbol in front of the larger number. So 7 is bigger than 2, so that would be a -5. So we have -5 squared over here plus 2 minus 8 is -6. And we'll square that, plus -6 minus 3. So if the symbols are the same, then what we do is we add and keep the symbol, so that would be a -9. And again, it makes sense if you think about a number line. On a number line, if I were to start at -6 and then subtract 3, so I go 3 spaces to the left, then I would end up at -9. Okay, all right, so just continuing here, this is going to give us -5 times -5 is +25, plus -6 times -6, because we're squaring it, is +36, plus -9 times -9 is +81. So we have, let's work that out over here. 81 plus 36 plus 25. So that's 7 plus 5 is 12. Carry the 1. That's 9 plus 3 is 12 plus 2 is 14. So we have 142. So we have to take the square root of 142, which will give us approximately, squiggly lines means approximately, 142, and we take the square root, so that'll give us about 11.9. Here's the tenths place. This is a 1 over here, which means that if we're rounding to this digit will stay the same. So that'll give us approximately 11.9. Okay, and there's our answer. So if we were to actually draw these on a 3-dimensional grid, and if we actually made that grid and we had a ruler and we actually took a ruler and measured it, it would be about 11.9 units from one point to the other. All right, that is it, and have a great day.